Hi to everybody. I hope you are very well where you are. As far as this course is concerned, PHYV 102 is concerned, we are going to start with chapter 23, and chapter 23 is about the electric fields. Now, there are many things that you will be able to know after completing this chapter, and these are, for example, the first one is you will be able to distinguish between conductors, insulators, and semiconductors materials. And you'll also be able to derive Coulomb's law or define Coulomb's law from his experimental observation. And you'll also be able to define the unit of charge. And you'll also be able to define an electric field. You will also know the superposition principle for electric fields and force. And you'll also be in a position of explaining the nature and purpose of electric fields line. And you will also be able to predict the motion of an electric charge in a region of electric field. And you will also be able to solve the problems on the above concepts. Now, why are we studying the electricity and magnetism? It's because the laws of electricity and magnetism play a central role in the operation of many modern devices, such as your cameras, your laptops, your cell phone, your TVs, and many more. One of the reasons is because the interatomic and intermolecular forces responsible for the formation of solids are actually electric in nature. For an example, if you consider the formation of sodium chloride, the formation of sodium chloride is actually formed from the positive ion of sodium as well as a negative ion of chlorine. So as you can see, these are definitely electric in nature. All right. Now, the concept of force links the study of electromagnetism to previous studies. It really links this study to other studies, as you will see when you compare the electric force as well as the gravitational force. Now, the electromagnetic force between charged particles is one of the fundamental forces of nature. For an example, you have already studied or you have already done one of the fundamental forces of nature, which is nothing else but the gravitational force. So this is the force that we have already studied in your first semester. So now in this chapter, I'm going to introduce you to the what you call the electric force, or the Coulomb's force. Right. Now there are two kinds of electric charges, and which are positive and negative. And negative charges are the ones possessed by electrons, while the positive charges are the types possessed by protons when you consider your atom. And of course, the like charges always repel, but the charges of opposite side will always attract each other. For an example, say you bring this negatively charged rubber to very close to the glass rod, which is positively charged. Therefore, the force between these two will just be attractive force. However, if you bring this negatively charged rubber close to another negatively charged rubber, then these two will just repel, because like charges always repel. Now, electric charge is always conserved in an isolated system. For an example, charge is not created in a process of rubbing two objects together, but the electrification is due to a transfer of charge from one object to another. For an example, when you rub the glass rod in the silk, what is going to happen there is the fact that the electrons are going to be transferred from the glass to the silk, and each electron adds a negative charge to the silk. An equal positive charge is left on the rod. The charges, therefore, the charges or the electrons are actually transferred from the rod to the silk. You cannot create no nor destroy the electric charge. Good. With that, let us just do the following quick quiz. Now it says 3 objects are brought close to each other, 2 at the time. When object A and B are brought together, they repel. When object B and C are brought together, they also repel. Which one of the following statement, or which of the following statements are true? I will just pause a little bit to give you a chance to think about this. And object A and C possess charges of the same sign. Object A and C possesses charges of opposite signs. All 3 objects possesses charges of the same sign. One object is neutral. Additional experiments must be performed to determine the sign of the charges. Now, the correct answers are A, C, and E. Just think about it. Just straightforward. All right. Now, the electric charge, we use the alphabet Q to denote the electric charge. We use alphabet Q to denote the electric charge as our variable, because charge can vary with time. You'll see when we do the capacitance that charge is a function of time. Right? Charge is actually quantized, and we can just write it in terms of this simple equation where Q is equal to plus or minus NE. And then this N refers to an integer. You cannot have a fraction or a half charge. It is always an integer. Now, E is a fundamental unit of charge, and the magnitude of this charge is the magnitude of E is given by 1.6 times 10 to the power minus 19 coulombs. Now, when Q is an electron, therefore it's minus E, but when Q is a proton, it's positive E. Now, let me also introduce you to different types of materials, which are conductors, and you also have insulators, you also have the semiconductors. But let us just start with conductors. Conductors are materials in which some of electrons are free electrons, and these electrons are free to move throughout the surface of the material. They move freely without any problem. Good examples are good conductors, which are actually including copper and aluminum as well as the silver. Now, as a result, this kind of materials, because the electrons are freely move without any problem, therefore they are able to conduct the electricity. Now, when a conductor is charged in a small region, the charge redistributes itself over the entire surface of the material. Right. Now, while on the other side, the insulators are materials in which all of the electrons are bound to an atom, which means these atoms cannot move. As a result, insulators cannot conduct the electricity. And good examples of the insulators are glass and rubber, as well as a wood. Now, when an insulator is charged in a small region, the charge is unable to move because the charge is actually bound to an atom. It cannot move from one region to the other region of that material. Now, the last material that I want to introduce you to is the semiconductors. Now, the electrical properties of semiconductors, as its name states, it's somewhere between those of insulators and conductors. And good examples of semiconductors materials include the silicon and germanium. In short, the semiconductors only conduct the electricity under certain conditions. For an example, if you take the silicon wafer, you heat it at a certain temperature, it will be able to conduct the electricity. So for further understanding of the semiconductors, the difference between semiconductors as well as the insulators and conductors, please visit the the link on the YouTube. It's just a very short. It's only for 4 minutes YouTube video, which explains everything very well. Now, let us also talk about the charging by induction. Charging by induction is nothing else but you require no contact with the object, which is actually inducing the charge. For an example, suppose that you start with this very neutral metallic sphere. Now, it's neutral because the number of charges are the same. The negative charges as well as the positive charges are the same. Now, what happens when you bring the charged rod? For example, in this case, we bring the negative charge rod. Now, the electrons in neutral sphere are redistributed. As you can see, the electrons are redistributed because they are going to be repelled away from this negatively charged rod, while these positive charges are going to be attracted towards this negatively charged rod. Now, if you ground, what will happen? If you ground, some of the electrons will just escape through the conducting crown. Now, if you remove the crown, now you end up having lesser electrons compared to a positive charge. Now, as a result, the positive charge has been induced, which means this metallic sphere will then be positively charged. And we normally term this as the positive charge has been caused in the sphere or has been induced. All right. Now, let us just remove, if you remove the rod, these electrons will therefore arrange them or distribute themselves uniformly over the metallic sphere. This is very important in order for us to be able to understand the following next quick quiz. Now, the charge rearrangement in insulator is also possible because suppose that you bring the positively charged object or sphere next to the insulating material. These charges will rearrange themselves or align themselves accordingly. As a result, as you can see, the negative charges will be next to the surface, while the positive will be on the other side. However, if this was a negative charged sphere, the opposite here was going to happen. Now, in this case of the insulator, when you put the insulator in the region of the electric fields, you are actually inducing the dipole, because you are inducing the dipole, you are causing the dipole because you have negative as well as the positive positive charges. Now, let us do the following quick quiz from the previous lessons on the charging by induction. Now, this one states that three objects are brought close to one another, two at a time. When object A and B are brought together, they attract. When object B and C are brought together, they repel. Which of the following statements are necessarily true? Number A, object A and C possesses charges of the same sign. Number B, object A and C possesses charges of opposite signs. And number C, all three objects possesses charges of the same sign. D, one object is neutral. And E, additional experiment must be performed to determine information about the charges on the object. Now, the correct answer for this is E. We really need additional experiment in order to determine the information about the charges on the object. Just when I give you a chance to think about this, and if you still don't understand, please don't hesitate to ask me during our tutorial session on Tuesdays. Now, let me also introduce you to Charles Coulomb. Charles Coulomb was a French physicist who made a major contribution in the areas of electrostatics as well as magnetism. And he also investigated in areas such as the strength of materials and structural mechanics and many other fields of study. Now, Coulomb's law he actually used his Coulomb's balance in order to measure the magnitude of an electric force between two small charged spheres. He found that the force depends on the charges and the distance between them. Now, before I can actually give you the mathematical description of this Coulomb's law, just want to define to you what is the point charge, because from now onwards you will be hearing me talking about the point charge. Now, the point charge refers to a term or refers to a particle of zero size that carries an electric charge. Yes, and of course, the electrical behavior of electrons and protons is well described by modeling them as point charges. As point charges. Okay, good. Now, the mathematical equations for Coulomb's law is just given by this equation here, where Q1 is charge, it's point charge 1, and Q2 is point charge number 2, and it must be this R is the square of the distance between them. And the SI unit of a charge is actually named after Charles Coulomb, and is just given as C, and that C means coulombs, right? And you have a constant. This constant is defined in terms of this value given here in this units in here. Now, this value is obtained by dividing 1 divided by 4 pi epsilon naught, where epsilon naught is the permittivity of free space, and the value for permittivity of free space is given as 8.8542 times 10 to the power minus 12 coulomb squared per newtons per meter squared. Right. Now, what I want to show you is also that this electric force between two charges is exactly the same as the gravitational force that you have done in your previous semester. But the difference here is Q1 is charges, but whereas the gravitational force, you've got the masses between two objects. And what I also want to say about these coulombs or the electric force is the fact that you really need two charges. You cannot have electric force when you have only one charge. You cannot have gravitational force only if you have only one mass. Therefore, gravitational force, you must have two masses. The same thing applies with the Coulomb's law or the electric force. That is, you need two charges in order for you to be able to have the electric force. And of course, if these charges are the same, then it's repulsion. But if these charges are not the same, then the force is attraction. Right. Now, remember, the charges needs to be always in coulombs. They must always be in coulombs, and because in most cases or in most problems, you will be given the charges in terms of microcoulombs, or they can also be in nanocoulombs. And you must always remember to use the prefix in terms of when the coulombs is actually, when the value of the charge is given in microcoulombs or nanocoulombs. And in your book, in the very first page, you just check the different prefix for different cases. Now, in this case, you must also remember that the force is a vector quantity. Now, what is also important in this slide is the fact that in order for you to have 1 coulomb, you need 6.24 multiplied by 10 to the power 18 electrons or protons. I just want you to see that you really need many electrons or protons in order for you to have one coulomb. All right. Now, here is just a summary of a table for the electrons and giving the charge, and as well as the mass, and for electrons, protons, and the neutrons. And from this table, we can eventually be able to calculate the gravitational force between the electrons and the protons, as long as we know the distance between them. And we can also be able to calculate the electric force or Coulomb's force between the electron and the proton, as long as we know the distance between them. All right. Now, based on the fact that force is a vector, This is the vector notation of a force, where this R is nothing else but it's just a unit vector pointing in the direction of that force. And I must also state the fact that F12 is just the same as F21, regardless of the magnitude of these charges, even if this charge can be bigger than the other charge, but the F12 will always be the same as F21. Why that is the case is because in order for you to have the electric force between these two charges, or the Coulomb force is actually the product of these two charges. When you have only one charge, you are not going to be able to have the electric force. All right, that's very important. Now, electric forces obeys the Newton's third law, as I've told you that F21 is just the same as F12, but they are in the opposite direction. As a result, you will have a negative sign here to just denote this other forces on the other different direction. And I've been saying that the like charges will always attract, whereas the opposite charges will always repel each other. Right. For argument's sake, let us just do the following problem of the hydrogen atom. Now, in this case, the electron and proton of a hydrogen atom are separated on an average by a distance of approximately 5.3 times 10 to the power minus 11 meters. Find the magnitude of electric force, and the gravitational force between the two particles. Now, the idea here, for us to be able to get the electric force, we need to know the charge between the electron and the protons. And now we will just use the previous table in order to get the charges between electron and proton. And in order for us to get the gravitational force, we will just have to use the mass of an electron and the mass of a proton, and the distance is just the same. And then from there, we just compare this force. Now, for electric force, this is what you are going to have for the electric force. And this is very important because this is just a constant and this is just the magnitude of the charge. Because the question was asking for a magnitude, there's no need for you to show the minus sign there because it's just the magnitude. And because the magnitude of proton and electrons are the same, you can just write 1.60 times 10 to the power minus 19 and then I square the number. Now, and 5.3 is just the distance, but remember there's a square. There's a square, that R must be square. Now, this is going to be the answer. And the other most important thing is that you must always remember is to use the significant figures very appropriately. For example, look at how many significant figures this number has. You've got 4 significant figures there, and then here you've got 3, and then here you've got 2 significant figure number. As a result, from this multiplication and division operation, the least significant figure is 2. As a result, your answer should be having 2 significant figures. So that is your electric force. Now, suppose you've been asked whether is this force attraction or repulsive force. Now, the answer will be the force will be attractive. Why? Because the charges there are not the same. Now, with this information, we can be able to tell. But however, remember that the question was just asking for the magnitude. As a result, you are not going to see the minus sign here. Now, let us also calculate the gravitational force. The gravitational force, we know from your first semester that G is just a constant given by this value. Now, we know the mass of electron, the mass of proton from the previous table. Now, you can eventually be able to plug the values, and then the answer would just be 3.6 times 10 to the power minus 47 Newton. Now, when you compare or when you take the ratio between the electric force as well as the gravitational force, you can see that you can eventually be able to see that the electric force is much greater than the gravitational field. Now, as a result, when we talk about the electrons and protons, there's no need for us to talk about the gravitational force because it's so small. It's so small. In fact, maybe this is one. In fact, this is one of the reasons why we have to introduce you to the electric force, because electric force is much greater compared to the gravitational force when we talk about the electrons as well as the proton or the charged particles of very less mass. All right, good. Now, let me also introduce you to the principle of superposition. Now, the resultant force on any one charge equal the vector sum of the forces exerted by the other individual charges that are present. What you need to do is to always remember to add the forces as vectors, because force is a vector. For an example, the resultant force when you have, say, four particles, or say 4-point charges, Q1, Q2, Q3, Q4. Now, the resultant force if the question might be asked that, what is the resultant force here? What is the resultant force of this particle F1? What is the resultant force of this particle? Now, the resultant force of the in Q1 will be the vector sum from this, and then it will also be added to that, and then there will also be a force between Q1 and Q4. So you just add them, you just add the vector sum of them, and then that will be the resultant force you will get in Q1. Right. We will just do the example in order for you to be able to understand this problem. Now, suppose that you are given this kind of problem where you have to find the resultant force. Now, consider 3-point charges located at the corners of the right angle triangle as shown in the figure, and the value of Q1 is equal to Q2, which is equal to 5.00 microcoulomb, and Q2 is equal to negative 2.00 microcoulomb, and A is just given as 0.1 meters. Now, the question is find the resultant force exerted on Q3. Now, as you can remember, this is a prefix which is equivalent to 10 to the power minus 6. You just have to use that, and even here. But here you are just given the distance between these charges in terms of meters. Then you don't have to change anything, because distance, that is the SI units of the distance. Now, the other thing that I need to say is the fact that you are not going to be given these arrows in order. You'll just be given this problem without these arrows, but you shall be able to come up with this direction of these forces. But the question is, we want to get the resultant force on this particle here. Now, if we consider Q3 and Q1, because they are both positive, they will repel each other. Then F13 is that force that is going to point in that direction. And of course, you will also have F31, which is the force that is going to be pointing on that direction. But for this problem, that is not important, because the question doesn't ask for it. Now, for Q2 and Q3, the force between Q3 and Q2 will just be the attraction, because it's got this charge is negative and this one is positive. Now, the force, because the question asks for us to get the resultant force on this charge, therefore that force will just be pointing on this other direction. The force on the F32 is just going to be the force pointing on the other direction there. Now, before I can actually do this problem, I also want to show you that this value here, you're not going to be given this value, but you can get this value from the theorem of Pythagoras. You remember, if you have a triangle like this, look at the whiteboard. If you have a triangle like this, this distance there, it can be defined in terms of x squared plus y squared. Now, if you take this, you use it in this problem here, you can eventually be able to show that this the distance between Q1 and Q3 is the square root of 2a, and note that this a is outside the square root. Otherwise, if a was inside the square root, it was going to be the square root of 2a squared, when that a is inside the square root. What I also want to discuss with you and then show you is the fact that this force F13 is got the x and the y components. It's got the x and the y components. For example, you have the F13x, you also have 13y because there's y components of this force F13, while F23 is got only the x components because you don't have the y components for this force. Now, as a result, or before we can even attempt to do this problem, I just want to also remind you of these three functions. Say you've got a triangle like this here. Now, if you know this angle here, theta, if you know this angle theta, the sine of the theta is just going to be given in terms of y divided by r, while the cos of theta is x over r, and the tangent of theta is just equal to y over x. And I hope you also remember that the tangent theta is just nothing else but just sine divided by cos, and then you can just prove that if you divide it by that, you just get this. So this is very important, and this is actually what I call the Socrates rule. Each and every time when I refer to Socrates rule, I will just be referring to this trigonometry functions that you know that you have done in your high school. Now, let us just compute this force. The first part will just be for us to determine the magnitude of these forces because we know the distance between them, and then we are given the value of A, we are given the value of Q2. If we also know the value of Q3, we can be able to tell what is this F23. Now the F23 is just given by this equation here, because you've got Q2, you've got Q3, you know the distance between them, and the final answer would just be 8.99. Now, look at the significant figures. The significant figures is 3 because the least significant figure in this operation of multiplication and division is 3. So this is what you are going to have. Please always remember to put this square. If you don't put this square, you are always going to get the wrong answer. Now, we've got this F23, and that F23 is nothing else, is just the F23x, and you don't have the y components of this force because it is only in x direction. Now let us also do the F13. Now if we do the F13, before I can just do that, I must also remind you that, remember, in the equation, this force, the magnitude of this charge was minus 5 times 10 to the power E. It was minus 5.00 microcoulomb. Therefore, as a result, this force must be negative 8.99. So that you must just have a minus there, which this minus, it just tells us about whether it was attraction or repulsion. And in this case, because the charges are of different sign or opposite sign, therefore it must be attraction. So negative sign implicates that this is an attraction force. Now for Q1 and Q3, for Q1 and Q3, this is what you are going to have as this the resultant force, this force here for 113. This is what you are going to have, and that's what you are going to have, 11.2 Newton. Now from this, we can eventually use the Socrates in order to get the F13x, and then in order to also get the y components of this F13. Now if you do that, the x component of the F13 is just given by this equation here. Now the angle there is 45, and there's nobody who's going to tell you that the angle is 45, but this is just a 45. I mean, if you draw your y and your x axis, this is the repulsion force between Q1 and Q3 will just be directed at an angle of 45. So the y component is just given by that value there. Now you just have to add the x components, as well as the y component in order to to get the resultant force. Now, if you add the x components of that force, the x component is the x component then, and then that F23, because F23 is only in x direction. So that is what you are going to have. And it is also very important to know the sign here, because if this sign, and also the direction of the force, because the direction of the force of F13 is in this direction, whereas the direction of F23 is on the opposite direction. As a result, you have to use the negative sign there. So as a result, this is what you are going to have as the x components of the force. And the y component of the force is only the 3y, the 3 1, the F1 3y. Therefore, that's your y components. Now, the resultant force is just in a vector form, is just given by this. Now, you can eventually be able to get the magnitude of this force. Now, the magnitude of this force is just the square root of the square of that. That will be the magnitude, and you can eventually be able to get the direction, and the direction of that. Then you just use the tangent of the angle theta, which is actually 45. No, you just use the tangent of the angle in order for you to be able to get the resultant direction of that force. Right. Good. Now let us also do the following problem, where it's asking where is the net force, where is the net force zero, where is the net force zero. Now this problem, it states that 3-point charges lies along the x-axis as shown in the figure. The positive charge Q1 is given by that value 15.0 microcoulomb, is at x is equal to 2.00 meters. The positive charge Q2 is equal to 6.00 microcoulomb, is at the origin, and the net force acting on Q3 is 0. What is the x coordinate of Q3? Now, for the x coordinate of Q2 to be 0, it means that the force between Q2 and Q3, the electric force of the F23 and F13 must just be equal. Now, if these forces are equal, therefore there will be no force on this Q3. Now, how do you do that? You just apply the Coulomb's law. But I must also state the fact that you are not going to be showing this in the equation. This is what you just have to think about it. But now, if you know the distance where the Q1 is being placed, it's 2.0, and you will just say, right, because I don't know the value of x at which Q3 is being placed, I will just call that x from the origin. I will just say from the origin to where Q3 is placed, that must be x. And now if that must be x, and if the length from there to there is 2.00 meters, therefore this distance from here to there, it must be 2.00 minus x. So that's what you will just have to think about, because you are not going to be given that. Right. Now, let us just apply the Coulomb's law. Now, if you apply the Coulomb's law, that the sum of all the forces from the principle of superposition, the sum of all the forces from the principle of superposition, it must just be the algebraic vector sum of these individual forces. Now, in that case, that must be equal to 0, because this Q3 does not move. Now, as a result, this F23 is just given by Q3, and then you've also Q2 and Q3, and then you've got X, because that is the distance between Q3 and Q2. Now, for the F13, the distance between F13 is 2.00 minus X, but that must be squared. Now, if you rearrange that equation, and they are all in x direction, because the force is a vector, they are all in x direction. If you rearrange that equation and you solve for x, In fact, what I want you to see is the fact that even if you were not given the value of Q3, you really don't need to know the value of Q3, because Q3 will just cancel in this equation. Q3 will just cancel in that equation, and rearranging the equation, this is what you are going to have. And when you solve for x, this is what you are going to have when you solve for x. And when you plug the values, you are just going to get x as 0.775 meters. Right. Now let us also do this example. Find a charge on the sphere. Find the charge on the sphere. Now in this case, when you've been asked to find a charge on the sphere, now this problem reads as follows: two identical small charges sphere, each having a mass of, you are given the mass, and is actually hanging in an equilibrium as shown in the figure. The length L of each string is 0.150 meters, and the angle theta is 5.00 degree. Find the magnitude of the charge on each sphere. Now, remember, what is very important here, they are in equilibrium. If they are in equilibrium, it means that they are not moving. As a result, we will just have to have the free body phase diagram. And in that case, if I only consider this particle or this point charge on my left-hand side, the free body diagrams tells me that you have the gravitational force going down, and then that side you have the force called T cos theta from the theorem of from the Socrator rule. If that angle is theta, therefore that angle must also be theta, because they are alternating angles. They form Z. They form Z. Now in that case, this force opposite to the gravitational force is just going to be T cos theta. And you also have the electric force on this other pointing on this other direction because of the repulsion from this other charge, and that must just be equals to this other force due to tension, which is nothing else from the Socrator, is T sine theta. But in order for this to be in equilibrium, now the sum of all the forces in X must just be equals to 0 in order for this charge to be in equilibrium, and all the sum of the forces in Y components must also be equals to 0. Now as a result, this is what you are going to have for the sum of the forces in X, as well as for the sum of the forces in Y. Now the question is, how are we going to be able to determine the Fe? Because we don't know the tension. We don't know the tension. How are we going to be able to determine the Fe? But from the trig functions that I've already written for you in the whiteboard here, remember, when the tangent of the theta is just given by this value here, is just given by the cos, the sine theta divided by cos of theta. Sorry, that must be a theta, not 0. Now, if you divide that, therefore you will get the tangent of the theta given by that. As a result, you will then be able to get what is Fe. If you divide this by that, then you see the tensions will just cancel. We really don't need to know the value of the tension, because if we divide that by that, we then cross multiply, then we will be able to know what is the Fe. Now this is the following. The Fe can be determined in terms of mg tangent of theta. Now we know the mass, we know the g, we also know what is the angle theta. All right. That this one was not going to help us because we don't know the tension. Therefore, we just divide that. But now, when you look at this diagram, we can be able to tell what is the sine of theta, so that we can be able to tell what is this A, what is the length A, because we don't know what is the length A. The length A is just given in terms of L sine of theta. All right. Now, if you go back, or you you use the Coulomb's law, you use the Coulomb's law because these charges are of the same sign, and you rearrange from the Coulomb's law because you will have Q squared instead of having Q1 or Q2. You just have Q squared. Now, if you rearrange, this is what you are going to have. And then when you plug all, because you know what is r squared, but r squared in this case, what is r squared in this case? R squared is the distance between these two charges. The distance between these two charges is 2a, because from here to there it's a, and you also have another a there, therefore you've got 2a. But we know the value of a. What is the value of a? The value of a is this, and we know the length, and we also know the length, and we also know the length of the string. Now, as a result, so when you plug the values in this equation that you have obtained there, this is what you are going to have. And also, please note the significant figure. Significant figure is also very important. Now, let me introduce you to the electric field. Now, the electric force is a field force. Field force can act through space. The effect is produced even with no physical contact between the object. This is what we have seen when we were discussing the the the, the induction, charging by induction. Now, Michael Faraday developed the concept of a field in terms of the electric fields. Now, an electric field is said to exist in the region of space around a charged object. This charged object is the source charge. Now, when another charged object or the test charge enters the region of an electric field or electric force acts on it. Right, I will just show you. By definition, the electric field is defined as the electric force on the test charge per unit charge. So that's the mathematical description of the of the of the of the electric field. So that is your definition of your electric field. You define the electric field in terms of the force and in terms of the test charge. Now, the electric field vector at a point in a space is defined as the electric force acting on the positive test charge Q naught placed at that point divided by the test charge. Right. Now, the electric field is produced by some charge or charge distribution separated from the test charge. The existence of an electric field is a property of the source charge. If you don't have a source charge, therefore, you are not going to have the existence of the electric field. Now, in this case, the test charge serves as a detector of the field. If the test charge experiences the force, whether attraction or repulsion, and it will also, for example, if we consider the test charge to be positive, then if the test charge experiences a certain force or repulsion, or we will just know that the source charge, which is responsible for the field, is positive. But when the positive test charge, experiences the force of attraction, we will be able to know that the source charge is negative. Right. This is what I am just trying to say here. Now, suppose that you have a wall here. You are not able to see the source charge. You only have this test charge. Test charge is denoted by Q naught, and the source charge is Q. Now, in this case, if you bring the test charge close, the moment you experience the electrostatic force of repulsion, then you can eventually be able to tell that the source charge on the other side of the wall is actually positive. But if the force on the test charge was attractive, then we're going to be able to know that the source charge is negative. Now, the SI units of electric field is just given by newtons per coulomb. Now, we can also say that an electric field exists at the point if a test charge at that point experiences an electric force. Right. Now, we can rearrange and write the relationship between the force and electric field in terms of this equation here, from the definition of the electric field. But this is only valid for a point charge, only. Remember the definition of the point charge. Now, the one of a zero size, for example, is very small. For example, the electron or the proton, for an example. But for large object, the field may vary over the size of the object. Now, if Q is positive, the force and the field are in the same direction. But if Q is negative, the force and the field are in the opposite directions. Now, based on the fact that the Coulomb's law is given by this equation here, the Coulomb's law is just given by that equation for this problem there. The Coulomb's law will just be given by this equation here, where you have the source charge and then you have the test charge. Now, if we rearrange or apply the fact that the electric field is given by this, you will end up with this equation that the electric field is just given by this equation here. The constant times the source charge divided by r squared. That is the electric field of the source charge. Now, for you to get the electric field, you only need one charge. You only need one charge for you to get the electric field. You don't need two charges like you need in order for you to get the electric force. Good. Now, when Q is positive, the force is directed away from Q. When Q is positive, the force is directed away from the Q naught. Now, the direction of the electric field, say you've got the point P somewhere, you've got the point P somewhere. Now, in that case, you have the source charge Q. You want to measure the electric field at point P. Now, if the charge is positive, now the field at point P is always away from the positive source charge. Now, instead, when you have the negative source charge and you have the test charge, the force will always be towards the source charge, as I've already discussed. Now, instead, you have a point P there. You also want to measure the electric field. Now, the field is always towards the negative, the negative source. Right. Good. Now, let us also do the following quick quiz, which states that the test charge of plus 3 microcoulomb is at the point P, where an external electric field is directed to the right and has a magnitude of 4 multiplied by 10 to the power 6 newtons per coulomb. If the test charge is replaced with another test charge of minus 3 microcoulomb, what happens to the external electric field at point P? The test charge, the Q naught, is not going to influence any electric field at point P. But what is going to influence the electric field at point P is the source charge. Right. Now, the correct answer for this is just A as a result. All right. Now, in terms of the superposition principle for the electric field, it's at any point P, the total electric field due to a group of source charges equal the vector sum of an electric field of all the charges. Now, I've already noted this in your whiteboard here. For example, say you've got the point charge, you've got the point P there. This is not a point charge. You've got point P, but we want to calculate the electric field. What is the electric field at point P when you have the 3 charges? And the first charge is situated there, and the other one is situated there, and the other one is situated there. Now, what does the superposition principle tells us is the electric field here would just be due to the electric field from Q1 and the electric field from Q2 and the electric field from Q3. The vector summation of all that will just give you the total electric field. And we will just do the one example in order for us to understand what is happening in this case. Right? Yes. Now, find the electric field due to two charges. Now, in this diagram here, Q1 and Q2 are located on the x-axis at distances A and B, respectively, from the origin as shown in the figure. Now, question A needs you to find the components of the net electric field at point P, which is at position 0x and distance y. Now, in this case, in order for you to be able to calculate the electric field due to Q1, you need to know this distance R1. The distance R1, if you know that this distance from there to there is y, you can just use the theorem of Pythagoras. You can just use this theorem of Pythagoras in order for you to be able to get that distance R1. Now, you will also do the same. You'll also do the same to get R2. Note that R2 is just going to be that and that. Now, I'm just want to show you the fact that the resultant electric field in that case, as you can see, the resultant, this is the E1. The E1 is just going to be pointing away from this point P, because the source charge, the Q1 is positive, but the E2 is just going to be pointing towards the Q2, and the resultant electric field will be somewhere between there. Now, as you can see that you have the X component for E1, and you also have Y component for E1, and you also have the X components for E2, you also have the Y components for E2. Right, that's what I'm saying. Now, let us just apply the Coulomb's law. Now, if you apply the Coulomb's law for E1, this is what you are going to have for E1. E1 is just going to be given by this. Remember, the E1 is just that. Now, if we want to get the X and Y components of the E1, then we'll just have to use the Socrator. And the angle between E1 and the x-axis is just phi, and then angle between the x-axis and E2 is just theta. Now, in that case, that is what you are going to have. Now, for E1, you are just going to have the x component in terms of the cosine of phi, and then you also have the y component in terms of the phi. So that is the E1, the x component and the y component of the E1. Now, in terms of the E2 from the Socrator, this is what you are going to have. Now, what is very important is the fact that here is B, because the distance there is B. Now, the R2 is nothing else but the R2 square is equals to y square plus B square. The same thing for R1. R1 square is A square plus Y square. So that is why you see these values instead of R1. Good. Now, in that case, that will be, therefore, the resultant electric field, you will just have to add the X component as well as the Y components of this in order for you to be able to get the resultant electric field. Now, what is very important is to know that this Y component for the E2 is negative, because the electric field for E2Y is negative, is pointing in a negative y direction. Now, in that case, the resultant, the EX, the X component of the electric field is just given by this equation here, because you're just adding that to that, and the Y component is just given by that to minus the other one. So that is your X component and the Y component of your electric fields. Now, question number B states that evaluate the electric fields at point P in the special case where Q1 is equal to Q2 and A is equal to B. I want you to know that if A is equal to B, that angle phi will just be equal to angle theta, and the electric field will just be along the the x-axis. Now in that case, we don't have to repeat the same thing because we already know what is the x and y, the components of the electric field. What we have to do is to just replace this B with A, and then we replace B with A or A with B, and then substitute. And this is what you are going to have in that case. So in that case, you just replace that, and then you also replace theta with phi, because that angle would just, theta would just be equals to E equals to phi. Now in that case, this is what you are going to have, because A is equals to B. Then the moment you see B, you plug this. Now the x components from the previous equation that we have obtained is just going to add this 2. You are just going to be able to add this 2, because now in this case you have only theta. There's no phi anymore, because angle theta is just the same as the angle phi. Now in that case, you are going to have a factor of 2 here, because these are just the like terms. Now also for the y components, however, will just cancel each other. The y components of this force of the electric field, sorry, will just cancel each other, because the other one is just going to be pointing on positive direction, and the other one will be pointing on the negative direction. So as a result, you don't have the y components of the electric field. You only have the x component of the electric field. But then, what is the cosine of theta in this? When you use the soccer term, the cosine of theta, because this angle here is also equivalent to theta. Why it is theta? Because of the alternating angles. Therefore, that angle, if that angle here is theta, therefore that angle is also theta. Therefore, in that case, the cosine of theta is just given by A over R. Now, what is A over R? We know what is A over R. Then we can eventually be able to replace the R. The R, remember, R squared is equals to A squared plus Y squared. But the R is just the square root of A squared plus Y squared. Now, we're going to plug this in that equation. Now, if you plug that in that equation, this is what you are going to have as your x component of your electric field. All right. Now, let us also talk about the electric field line. Electric field line gives us a means of representing the electric fields pictorially. It's not a material thing. The electric field vector is tangent to the electric field line at each point. The line has a direction that is the same as that of the electric field vector. The number of field lines per unit area through a surface perpendicular to the lines is proportional to the magnitude of the electric field in that region. Now, for the positive charge, this is what you know from your high school. The field line radiates outwards in all direction. So the lines are always directed away from the source charge. A positive test charge will repel away from the positive source charge. Right. Now, in terms of the negative charge, the field lines radiates inwards. They radiates inwards, or they radiate into the charge. The lines are directed towards the source charge, and the positive test charge will be attracted towards the negative source charge. Now, if you have the two charges of opposite signs but of the same magnitude, the charges are equal. The number of field lines leaving the positives must just be the same as the number of lines entering the negative charge. Now, the charges are equal and opposite, therefore that will be a repulsion. And I also want us to do this a quick quiz whereby you are requested to rank the magnitude of the electric field at points A, B, and C shown in the figure. You need to align them in terms of the greatest, which one is the greatest and which one is the smallest. Now, in that case, A must be the greatest and B must be the next one, but C must be the lowest because there's no field lines which are passing C. All right, good. Now, in a case where the positive charge is greater, is twice the magnitude of the negative charge, two lines leaving the positive charge for each line that terminates on the negative charge. At a greater distance, in a very far away, the fields will be approximately the same as that due to a single positive charge when you are very far away from these two charges. Now there are rules on drawing this field line. The lines must begin on a positive charge and terminate on the negative charge, as we have seen. Now, the number of field lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. No two field lines can cross each other. Remember, the field lines are not the material or objects. They are just the pictorial representation which is used to quantify or quantitatively describe the electric fields. Now, the motion of the charged particles, this is the last section of this chapter, the motion of the charged particles in the region of the electric fields. Now, when a charged particle is placed in an electric field, it experiences an electric force. Now, if this is the only force on the particles, it must be the net force. For example, we have seen that the gravity is very small, and then as a result, we can end up ignoring the gravity. Now, the net force will cause the particle to accelerate according to the Newton's second law. Now, from this equation of the force, we know that the force is just given by this, and if this is the only force, therefore it must just be equivalent to the Newton's second law, which is F is equals to ma. Now, if electric field is uniform, then the acceleration is constant. If the particles has a positive charge, its acceleration is in the direction of the fields. If the particles has a negative charge, its acceleration is in the direction of opposite to the field. Now, since the acceleration is constant, the kinetics equation can actually be used. Now, I just want to show you this. Just want to play you this simulation before I can pause, so that we can all understand what is happening when you put these charged particles in the region of the electric field. All right, good. Now in this case, I just wanna take it up, and I must also take it push up a little bit. Now in that case, say you have a positive charge here, and then this positive charge is actually, I want to launch this, I can be able to change the speed at which I put my positive charge there, and I can also change the field strength. What does that mean? I can actually change the polarity of this plate here. I can either make it to be positive or negative. For example, just want to change this plate to reverse the charges. See, I can reverse the charges, and I can also play with the field strength, the electric field strength. Now, in this case, let us just, for argument's sake, let us just launch this positive charge at the highest velocity, and then see what is going to happen. Now, when we launch this positive charge, do you see this charge is going to divert to the side of this negative plate? That's what is going to happen. Now I can change the polarity of the charge, and I make it negative charge. Now if it's the negative charge, and then I launch it, the moment I launch the negative charge, the moment it reaches the region of the electric field, it will experience a force, and it will divert into the positive side of this plate. Now, suppose that I can also make this charged particle to be, this particle to be neutral. If it's a neutral particle and then I launch, do you see? a neutral particle is not going to get any influence or affected by the region of the electric fields. And I must also say that this is what is happening at the temper labs, where they are controlling the charged particles. For example, in the hospital side, where they are using the protons to cure or the tumor cancer. So this is what is happening in order to direct the protons from the accelerator side to the hospital side. Right. Now I also wanted to perhaps I must just pause here and stop our our lecture our lecture just right here. But before I can actually stop the lectures, I just wanted to show you the very last slide of our lecture, where you are actually given the tutorial problems that you need to do. Please, this is only in the 9th edition, though those 5 tutorial problems, and we will discuss them in during our tutorial session on Tuesday. And I would like to therefore pause here for this chapter. Bye bye and keep well. Bye. See you next time.